Hello everyone. So in this video, I'm going to discuss the third problem which came in BMath BStat 2025. Yes, I've been solving the problems and posting the solution. Like the first and the second is done. Now time for the third one. What is the third problem telling us? That is, suppose you have a function whose domain is closed and boundary interval 0, comma 1, and the codomain is R. And it's differentiable where the function is taking at 0, it's taking the value 0, and f of x is always for in its domain it's greater than or equals to mod of f dash x. We have to show that the function is like 0 throughout its domain. Okay, so now you have to notice something that is, like here, whatever be the value that the function is taking f dash mod of f dash x, so that is always greater than or equals to 0. Okay, and so we get that f of x is always taking the value greater than or equals to 0. So that means f of x is taking some non-negative real values. Always it's in its domain, it's taking non-negative real values. Okay, and what do we have to ultimately show? It has to be 0. So that means we have to show that it cannot take positive values. Okay, so what if, like, and also we know that since the function is given to be differentiable in its closed and bounded interval 0, comma 1, so we know that the function is also continuous in that closed and bounded interval 0, comma 1. And while we learned continuity chapter, so we also learned that any continuous function on a closed and bounded interval AB, so attains its maximum at some point and its minimum at some point in that domain. So that means what we can say is that if we somehow show that the maximum value that the function is attaining in that interval closed 0, comma 1, so if that is 0, so that means then the function has to be totally 0 because it cannot take negative values. All the values are greater than or equals to 0, and the maximum value, if it is also like less than or equals to 0, so that means like I mean, if the maximum value is is equal to 0, so then the function will be like having values greater than or equals to 0 and also less than or equals to 0 for all x in its domain, and thus we will be able to prove that the function is like totally 0 in its domain. So that's the idea. Okay, and now let's proceed and prove it. So let's go to the whiteboard. Okay, so yeah, so this is question 3. And we have been given that f of x is always greater than or equals to mod of f dash x. And now this is greater than or equals to 0 for all x belonging to close 0, 1. Okay. So the function is taking non-negative real values. And now what? So we know that, like, suppose we define the maximum of the function f from the point 0 to y, any point y in its interval. Okay, in that interval 0 to 1. So let m of y be the supremum of the function x close 0 y. Okay, and f of x. Okay, and so this is we are taking it to be the supremum. So now those who don't know about what the supremum is, so just think of it as the maximum value the function is taking in that like if I further restrict the restrict its domain from close 0 to y. Okay, so now we know that, like, there will be a point where the function is attaining its maximum value. Okay, and now why am I taking it? Why don't I write it as the capital M? Why am I writing as M of y? So that maximum will depend on y. Okay, so y belonging to open 0 and 1 closed. Okay, so now at 0 the function is taking the value 0, so we don't have to work on that point 0. So we have to work on this interval, that is open 0 to closed 1. We have to show that the function is 0. So now try to understand that y depends on the maximum value depends on the point y, because suppose if I take the point y to be half, so the maximum value that the function is taking from 0 to half, and suppose then I take the y to be 1, So the maximum value that the function is taking from open 0 to 1 and open 0 to half. So these two maximums might differ. Okay. So that's why, like, we can say that, so that's why we are saying that the supremum or the maximum that the function is attaining in this interval, that is closed 0 to y, closed and bounded 0 to y. So that is m of y. Okay, that's what how we are defining it. Okay, and now since the function is continuous in this closed and bounded 0 to y, so we can say that, like, there exists x naught belonging to closed 0 y such that f of x naught is equals to m of y. Okay, so at the point x naught, the function is taking the maximum value. Okay, and now what we know is that, like, if x naught, okay, if x naught is, so case 1, so this is a trivial case, if x naught is equal to 0, so then we know that, like, f of x naught is equal to f of 0, which is 0, and thus we have that, like, f of x is greater than or equals to 0 because of this, and this is less than or equals to like m of y, and like, which is less than or equals to f of, or sorry, this is equal to f of x naught, and which is like f of 0, which is equal to 0. Okay, so in this interval, so for all x belonging to 0 to y closed. Okay, so now here what happens is that, so this would imply that our function f of x is, like, it's like f of x is greater than equals to 0, and also it's less than equals to 0. So what we can say from there, it's that the function is equal to 0 for all x belonging to closed and bounded interval 0 to y. Now try to understand that since y is any arbitrary point from 0 to 1, so that means, like, for all the points, like, so that means what, like, I mean, since y is y can be any value, any arbitrary value from 0 to 1, and we have that, like, the maximum value that the function is taking at x naught, so that that the maximum value is itself 0. So then, like, I mean, not the maximum value is itself 0. Why? Because like, the maximum value is being taken at the point 0, and the function is given that at the point 0 it takes the value 0, so automatically the function, the maximum value becomes 0, and thus we are done. That is the for this part only. Okay, for this trivial case we are done that the function is 0 in this interval. Okay, and it's not and it's like, since y is arbitrary, so it's the function is, like, totally 0, so this implies that f of x is equal to 0 for all x belonging to close 0 to 1, since y is any arbitrary point in open 0 closed 1. Okay, now what if the case 2, that is, we are taking that, we took here, that is x naught is 0. So if x naught is, so what if, like, x naught is strictly greater than 0 now, and it's less than or equals to y. Okay, so in this case what can happen? So in this case what we'll do is, so by mean value theorem, we can say that there exists theta belonging to open 0 x naught. So again, all the conditions of the mean value theorem are satisfying. Okay, so you can very well check that out. So there exists theta belonging to open 0 to x naught such that m of y, which is the maximum value of the function f of x from, like, in the closed and bounded interval 0 to y, so that is, like, equal to f of x naught And that we can also write it as f of x naught minus f of 0. Why? Because f of 0 is 0. And like that is equals to f of f dash theta times, now here we would be having x naught minus 0, which is basically x naught. So multiplying that x naught on that side. So x naught. So I'm getting this, that is, this is happening if that the maximum value that the function is taking from in the closed and bounded interval 0 to y, it's like equal to f dash theta times x naught. Okay, where x naught is that point where the function is taking the maximum value, and theta is any point where that mean value theorem is holding. Okay, so whatever happens, we can say that this is less than or equals to f of theta uh, times x naught. Okay, why? Because again, try to understand that we have been given that for all x belonging to 0 to 1, f of x is always greater than equals to mod of f dash x. So that's why we can say this. Okay, and now further, like try to understand that what is like f of your f of theta into x naught. So we can further work on it. Like we have m of y is less than equals to f of theta times x naught. Now f of theta I can also write it as less than equals to m of theta times x naught. So why? Because m of theta is means what? That the maximum value of the function in the closed and bounded interval 0 to theta. So now try to understand that theta is strictly greater than 0 and is strictly less than x naught, and x naught is less than equals to y. So what we have is that the function, the maximum value that the function is taking from 0 to y is less than equals to f of theta times x naught that we got from the mean value theorem. And again, whatever is the maximum value that the function is taking from 0 to x naught, so like so which is basically like sorry, so from 0 to x naught, whatever the maximum value that the function is, sorry, I'm making a mistake here. Yeah, so m of theta is basically like the maximum value of the function from in the closed and bounded interval 0 to theta, right? So now whatever like be the value of f of theta, so that will be like less than or equals to the maximum value that the function is taking from 0 in the closed and bounded interval 0 to theta. So that's why I can say that like f of theta is times x naught is less than equals to m of theta times x naught. And now I can also say that this is less than equals to m of y times x naught, because whatever the function is, the maximum value the function is taking from 0 to theta. So, and whatever the function maximum value the function is taking from 0 to y, so yes, 0 to y, so that is m of y. So m of y will be bigger, greater than equals to m of theta, because y is greater than equals to, strictly greater than theta. And uh, so here we can say that like further we can say that like this is less than or equals to m of y times, we can replace x naught by y as well, and thus we are getting here that is m of y is less than equals to m of y times y, which implies that m of y times uh, y minus 1 is less than equals to 0. So now if I have y to be strictly between 0 and 1, then I can say something here. So let's do something, that is what we can do is let's take y to be strictly between 0 and 1. Okay, so let's so here it was there, and now let's take here to be y to be strictly between 0 to 1. Okay, so even we can take it at the beginning as well, so it doesn't matter. So yeah, we took it here, that is y is from 0 to 1. So now let's do one thing. We don't want y to be 1. So that's why like what we will do is we will like we will use the continuity property to extend the function to 1. So what I am going to do is like here, since I'm taking y to be like strictly greater than 0 and less than equals to 1, so I'll still leave 1 as well. So I can say that like here let y be strictly greater than 0 and strictly less than 1. Okay. So I'm defining y to be strictly greater than 0 and less than 1. So it doesn't matter, right? So again, still the same thing, that is there will be some x naught in 0 to y such that f of x naught is m of y, because m of y is nothing but the maximum value that the function is attaining in that interval, closed and bounded interval 0 to y. So now I am safe and to go for this one and say that m of y will be less than equals to 0, since y is like belonging to strict open 0 1. Okay, otherwise like what would have been the problem, because y, if y is 1, so then like that becomes 0, and so we cannot conclude anything about m of y then. So that's why, to be on the safe side, like we want that m of y should be less than or equals to 0, right? So that's why, to be on the safe side, we like made it to be like y to be um, strictly between 0 and 1. Okay. So now what are we getting? That is the maximum value of the function is less than or equals to 0. So again, the same conclusion, that is f of x is greater than equals to 0 and less than equals to m of y, and which is less than equals to 0 for all x belonging to 0 to y closed. And now, since again, like, so that implies that f of x is equals to 0 for all x belonging to 0 to y. Okay. And where y is strictly between 0 and 1. And that implies that f of x is equals to 0 for all x belonging to 0 to 1 open. Why? Because since y is any arbitrary point in open 0 1. Okay. And so we are done like from 0 to open 1, like close 0 to open 1, the function we have proved it to be 0. Fine. Now what next? So this is x belongs to 0 to y. We have done it. Yeah. So now I have to extend it to 1 and show that the function is 0, and we will be done. So this we will use the continuity property of the function. Since the function has been given to be continuous, so try to understand, we'll just simply use the sequential criteria. Okay. So suppose this is 1. Now since the domain of the function is from 0 to 1, so if suppose there is, so let's take a sequence which is converging to 1, so we can only take it from the left hand side of 1 because the domain is from 0 to 1. Now at the point 1, we know that the function is differentiable, so it's continuous as well. So now if we take any sequence xn, okay, which is like converging to 1 as n tends to infinity. And now since the function is continuous at the point 1, so by the sequential criteria, we know that the sequence f of x n in greater than equals to 1 also converges to f of 1 as n tends to infinity. Okay. And now what do we know? That is, suppose the first value is x1, x2, and so on. So this is the sequence. Now, what is f of x1? We have already proved it to be 0. So x1 is a value between 0 and 1. And f of x2 is also like 0, and so on. So basically this function is a constant function. Why? Every term is 0. So a constant function goes and converges to that constant value 0. So this will go and converge to that value 0. So this goes to and converges to 0 as n tends to infinity. Now and also like from the like the sequential criteria of continuous functions, we know that it will go and converge to f of 1 as the function is continuous at the point 1. And now we know that a convergent sequence of real numbers cannot converge to two different values. It cannot have two different limits. So that implies that f of 1 has to be equal to 0. And we are done. So by the continuity of f at of x at x equals 1, we conclude that f of 1 has to be 0, and thus f of x is equals to 0 for all x belonging to closed 0, 1, and hence proved. Okay. So I hope I mean, it's clear like how I did it. And again, if you don't know, again, I'm saying if you don't know what the supremum like what that supremum thing is, so just think of it as the maximum. Okay. And we are done with the third problem. And again, if you are having problem in grasping the solutions, sorry, not grasping the solution, like grasping the concept. So give it time, like pause it, try it on your own, try it intuitively, like how the function is behaving. So gradually you will be able to absorb the thing, and also go and revise continuity, differentiability chapters, the theory that you have learned there. So then I mean, slowly it might take some time, but you will understand definitely. Okay. So again, if you found it like helpful, so don't forget to put a like. And again, yeah, I'll definitely try to post the solution. So yeah, it's already 3:39 a.m. in the morning, and I have to go to sleep. So I'll try and post the other solutions tomorrow as well. So yeah, so that's it for this video. So thanks for watching, and see you in the next one.